Now, another very common thing that's going to come up with the photoelectric experiment questions is graphing. And they do have a very distinctive graph shape. And what's unique about these ones here is that we're going to be using three pieces to the graph: the y-intercept, the x-intercept, and the slope of the graph there. And so we'll look at how these relate to the various equations. But a couple things just to remember. The y-intercept of the graph is always related to the work function. Now, sometimes it will be equal to the work function. Sometimes there'll be a little bit more to it. But you'll always be able to work the work function back, or work out the work function from the y-intercept. The x-intercept is always going to be in some ways related to that threshold frequency, if that's what's on the x-axis, or threshold wavelength, if you have, say, a wavelength on the x-axis, though in that case it's usually 1 over wavelength. And the last thing then, the slope of the graph is always going to be related to Planck's constant. And once again, it could be equal to Planck's constant, or it could be related to Planck's constant in a slightly more complicated fashion. So if you look at this first one, and this is probably our simplest derivation for these, the kinetic energy versus the frequency. Now the kinetic energy has to be for electrons because only particles can have that kinetic energy. And your frequency, again, is for the light, again, given by Planck's constant. And so what you have is you have the energy of the photon, and that'll be equal then to the work function plus the kinetic energy of that electron. So our kinetic energy is on the y-axis, so I'm going to isolate that kinetic energy in my equation. Now my photon energy is just going to be h times f, and I'll subtract the work function from there. And so what we see then when we look at our different pieces is on my y-axis I have this ek. My x-axis is this frequency, so anything multiplied by that x-axis has to be the slope. And that's why this h value then is the slope of the graph, and then anything added or subtracted to that term, that has to be then your y-intercept. And so what we see down here is we have our y-intercept, and that will be just equal to the work function in this case. We have our threshold frequency, which will be then the x-intercept showing up over here. And then the slope of the graph will be just equal then to Planck's constant in this case. And so we'll just take any 2 points on here, look at the change in y over the change in x, and then that will be then the slope of the graph, and that has to be equal then to h, which is Planck's constant. Now one other note about the graph here, you'll see that we have this dotted line here. Now this dotted line is just because there is no light actually here. This is an extrapolation. So remember, the threshold frequency is the minimum energy, or the minimum frequency of light at which electrons are emitted. So any frequencies that are lower than that aren't going to actually emit any electrons, so none of them will have any kinetic energy. So we can only get data points actually in this region here. This is an extrapolation, and it's a useful extrapolation because that will give us then the work function then for those ones here. On the other side then, we have now stopping voltage versus frequency. Now I'm going to jump straight to this version of the equation here. So we have Ek equals Hf minus the work function. But what I'm going to do now is I'm going to substitute that QV stop in for the Ek, and that gives me then Hf minus W. Now if I want to isolate my voltage, which is what's on the y-axis, I have to divide out that Q. So then I get Hf divided by Q minus W over Q. And don't forget you have to then subtract both of those terms. So once again, if we just separate out then the x and the y-axis, I have this voltage here, that's my y-axis, and frequency is still then on my x-axis. But what I see now is that multiplied by that frequency, which is the slope value, is h over q. So here's a case where the slope, again, is related to that h over q, but it's not exactly equal to that. So if I put in that slope value here, the slope is anything multiplied by the x-axis variable in my equation. In this case, that is h over q. And so I get a slightly more complicated equation for my slope. But my q is a known value. It's the 1.6 times 10 to the negative 19. So I can put in my slope value, multiply it by q, and that'll give me then the Planck's constant there. In terms of the work function, anything added or subtracted to it is going to be my work function. And so that's going to be w over q. So I'll have that divided factor then with the 1.6 times 10 to the negative 19. In this case here, though, if you put in 0 for your voltage, you will find then that your threshold frequency does still work out to be then the x-intercept. So your x-intercept does tend to be just the threshold frequency or the threshold wavelength. But if I am dividing out by other terms, your work function and your slope value will very often have other factors then put into here. And again, you could also put in then wavelength on the x-axis. That will give you a nonlinear graph. So typically what we'll put in is 1 over the wavelength then to straighten that curve.